Hi all. In the previous lecture, we tried to understand the system Deuteron, and we saw that it is a very weakly bound system, and most of the time it happens to be unbound, and sometimes the neutron and proton are close to each other so as to facilitate interaction via nuclear forces. Let's see the spin and parity of a deuteron. The measured value of nuclear spin of a deuteron is 1. And the parity, if we look at the parity, it is even parity. Okay, so the ground state of a deuteron can be represented as I pi would be 1 plus. Okay, so now we are going to see how uh, this nuclear spin is obtained and how can we explain for the occurrence of this particular spin value. We have never observed a deuteron with spin 0. Always the spin of deuteron is 1. So experimentally, we have observed that 100% the possibility is for occurrence of a nuclear spin value of 1. But if we are examining the theoretical possibilities, there are actually different possibilities which yield uh, spin of 0 also. Let's just go through the theoretical possibilities of nuclear spin. We know that proton and neutron, which are part of the deuteron, have spin of half. Spin half particles can either take upspin and downspin possibilities. So there are actually 4 combinations of spins like this. Both are upspin, both are downspin, and one is up, the other is down. There are 4 different options. Now, if you these 4 options can be written like this. Just you consider when both spins are parallel, the resultant spin is 1. When both are anti-parallel, the resultant spin is 0. So S equal to 1 can have 3 different projection values, which is plus 1, 0, and minus 1. So these 3 options can be taken as projections of S equal to 1 state. And for S equal to 0, you can have one value for Sz, which is this option. Okay. So theoretically, actually, uh, there are 3 possibilities which favor spin of 1 and one possibility which favors spin of 0. Now the total spin of a deuteron would be L plus S, right? Now since it is the ground state of a deuteron, L is equal to 0. So for these different S values, there is an option that I can be 0 or I can be 1, isn't it? L is always 0 because we are talking about the ground state. When we are talking about the ground state, when we have 2 different options for S, there are actually 2 different possibilities for I. It can either be 0 or it can be 1. When we theoretically say so, that 75% probability is for I equal to 1 and 25% probability is for I equal to 0. Why are we saying like that? Because out of 4, 3 favor S equal to 1 and only 1 favors S equal to 0 option. Okay. So theoretically there are 2 different possibilities, but experimentally we see that I is always equal to 1. So let's examine the different possibilities. When S equal to 1 and L equal to 0, I can be 1. Now, when S equal to 0 and L equal to 1, I is 1. When S equal to 1 and L equal to 1, I can have these 3 possibilities. And when S equal to 1, L equal to 2, I can have these 3 possibilities. These are the 4 options where you have I equal to 1 possibility coming out. Okay. Why are we taking only these options? Because we have seen that the measured value of nuclear spin for a deuteron is 1. So we are just listing out the possibilities where we can obtain I equal to 1. Another restriction comes in because the observed parity of a deuteron is always even. And we know that parity is evaluated as minus 1 raised to L, isn't it? So if this has to be a positive thing, this has to be a positive quantity, L has to be even. So we can actually rule out the possibilities where L is equal to 1. Okay. So these two possibilities are ruled out. Now what are we left with? We are left with two options where we have I equal to 1. Okay. It can be L equal to 0 or it can be L equal to 2. If it is a central potential that we are assuming, then there is no angular dependence. YLM is a constant. And then it is a pure L equal to 0 state. But if we are considering a non-central potential, then L can take other values also other than 0. So the best possible option is actually to take the state of a deuteron to be a mixture of both L equal to 0 and L equal to 2 states. Okay, so the spin of a deuteron and the parity of a deuteron tells us that the deuteron actually exists in an admixture of L equal to 0 and L equal to 2 states. Okay, because this possibility also cannot be ruled out by the spin and parity consideration. So our deuteron exists in a mixture of L equal to 0 and L equal to 2 states. There are other things also which support such such an option, and one such quantity is the magnetic dipole moment of a deuteron. Okay, assuming L equal to 0, then there should be no orbital contribution to the magnetic moment, and then the magnetic moment would be just coming from the spin of the neutron and spin of the proton. And we know these GSN and GSP values to be like this. And if we evaluate, we get a calculated value of magnetic moment to be 0.879804 nuclear magneton. But the observed value happens to be 0.857, etc., plus or minus this thing, this much mu n. Okay, this may seem reasonably close, but in the case of nuclear physics, when you are talking about precision of, you are talking about accuracy of, say, to the sixth digit. In that case, this these two values differ from each other. Okay, so this small discrepancy, this can be because of the initial assumption that there is no orbital contribution to the magnetic moment, or just because we took L equal to 0, that is why this difference has come. So if we consider that the state of a deuteron is a mixture of L equal to 0 and L equal to 2 state, then orbital angular momenta coming from L equal to 2 state will also contribute to the magnetic moment. And if we take like that, we see that there is an agreement in the magnetic moment values. So the best fit to the the observed value comes in when you calculate the magnetic moment as coming from both L equal to 0 state and L equal to 2 state. Okay, and the admixture should be in this proportion, that is, it's 96% L equal to 0 state and 4% it is L equal to 2 state. If you take the calculate the magnetic moment in this linear combination proportion, you see that the calculated value of magnetic moment matches with the experimentally observed value. Okay, now the next quantity is electric quadrupole moment. If we consider our L equal to 0, if we consider our L equal to 0, it just means, if you remember the case of a hydrogen atom, you know how your L equal to 0 state was. It was, say, spherical in shape, right? So, when you are considering that your deuteron is in the L equal to 0 state, it just means that the charge distribution is spherically symmetric, or your uh, quadrupole moment expected should be 0. If you remember our previous lecture, we had mentioned that electric quadrupole moment tells you uh, the tells you whether your nucleus is spherical in shape or not. So, if you are considering L equal to 0 state, you expect the charge distribution to be spherically symmetric, or you expect the nucleus to be spherical in shape, and therefore the electric quadrupole moment expected is 0. If you are considering, if we take our deuteron to be just L equal to 0 state, then the quadrupole moment expected will be 0. But when we measure the quadrupole moment, we see that it has a non-zero value. Its non-zero value indicates that the charge distribution is not spherical in shape. Now, if the charge distribution is not spherical in shape, it just means that it cannot be purely L equal to 0. If it is purely L equal to 0, then the charge distribution has to be spherically symmetric and the quadrupole moment has to be 0. But since the observed value indicates that the charge distribution is not symmetric, not spherically symmetric, it just means that your deuteron is not purely in the L equal to 0 state. It is a mixture of L equal to 0 and L equal to 2 in the proportion, it's 96% L equal to 0 state and 4% L equal to 2 state. Such an assumption gives us a theoretical value for the quadrupole moment, which matches quite well with the experimentally observed value of quadrupole moment for a deuteron. Okay, I hope this was understandable. Thank you.